Trends in the alkali metals. Need to talk about these, but I don't consider them super important. As you go down in this column, we've got increasing atomic radius, we've got increasing density and reactivity. So as we go down lithium through cesium, cesium's the most reactive. All of them have low ionization energies. They're good reducing agents because they're easy to oxidize. Very unreactive, generally soluble compounds in water. Remember, that was one of the things. Lithium, sodium, potassium, rubidium, all of those compounds are soluble in water. As far as reactions, they're very reactive. They will react vigorously with nonmetals such as the halogens. They form ionic compounds, and so we can predict the formulas for their compounds because we can predict the ions. So alkali metal is going to form a +1 ion. Here, if this is halogen, it's going to form a -1, and so we'll get Mx. Alkali metals react explosively with water. You put a lump of sodium in a sink full of water, bye-bye sink. It explodes. It generates hydrogen gas and a tremendous amount of heat, and enough heat that the hydrogen gas explodes, combusts, right? And no, I'm not going to do that demonstration in class. So I want to keep my job. So the metal reacts with water, and you're going to get hydrogen gas, the metal ion, and hydroxide. And there's pictures of these. Lithium is just going to kind of fizz around. Sodium is going to generate hydrogen and enough to combust that. Now that's a little tiny piece of sodium. And here's potassium. Potassium is more reactive, and as you go down, they get more and more reactive. Trends in the halogens. Going down a column, we've got increasing atomic radius, density, increasing melting point. We've got decreasing ionization energy and decreasing reactivity. So the alkali metals got more reactive as you went to the bottom. The halogens become less reactive. Halogens have very high electron affinities, so they're good oxidizing agents because they're easy to reduce. And this is why the alkali metals and the halogens react together so well, because one of them's like happy to give up electrons and the other one's really happy to take the electrons, and so they react together very well. These are also very reactive and generally not found uncombined in nature. Their compounds are also generally soluble in water. The reactions of halogens. So they're going to react with metals to form metal halides. Now, if this is a predictable metal, a metal with a predictable charge, we can predict the formula. If it's a transition metal, not as easy to predict. They will react with hydrogen to form hydrogen halides. So these are in the gas state. If this was in water, this would be an acid. So hydrogen chloride, hydrogen bromide, etc. I believe that this is a picture of the reaction of sodium with chlorine. Forms sodium chloride. So these sorts of questions can be a little bit challenging. Write a balanced chemical equation for each reaction. The reaction between aluminum metal and chlorine gas. Well, let's just see what we can do with this. So we need the reactants, right? Aluminum, solid at room temperature. And metals are never diatomic. We've got chlorine gas, Cl gas. Is that one of the diatomic elements? Yes, it is, Cl2. And so then we have to think, well, what kind of a compound is this going to make? Well, we've got a metal and a nonmetal. It's going to make an ionic compound. And the formula comes from the charges. So what kind of an ion does aluminum make? 3+. And chlorine? -1. So we're going to get AlCl3. Now, is that going to be solid, liquid, or gas? Ionic compounds have very high melting points. What state is sodium chloride at room temperature? Salt. Table salt. It's a solid, right? I can't think of any ionic compounds that are not solids at room temperature. Notice that there's no water involved here. This is not an aqueous solution. So then we have to balance the equation. We've got 1 aluminum on each side, but we've got 2 chlorines on one side and 3 on the other. So if we double this, we can get rid of that odd number. Now we've got 6 chlorines, 3 molecules there, and 2 aluminums. So if you're presented with a question like this on an exam, it can kind of freak you out. But you know this stuff, right? We've learned how to predict formulas. This is back in chapter 3, I think. Predict the formula for the compound formed between aluminum and chlorine. We did that. So we can do it here too. Okay, lithium metal and liquid water. So there's lithium and liquid water. Okay, H2O, liquid. And then what's going to happen? Well, now this requires maybe a little more remembering of stuff. The alkali metals react explosively with water. And it's explosive because it generates hydrogen gas and a lot of heat. And the heat causes the hydrogen to burn. And so miniature Hindenburg in the sink, right? So alkali metals reacting with water, we're going to get hydrogen gas. So we're going to get H2, and that one you kind of have to remember. Well, lithium and nonmetals of some sort, what kind of a compound is it going to form? Molecular or ionic? Ionic, right? So the lithium is going to have a +1 charge. And we've got H2O here. So, like I said, this one's a little harder than that first one. What's the anion? Well, you could imagine 2 things coming out of this, right? You could say, well, I took the 2 hydrogens off. It must be oxide. That's not true. It's hydroxide. So that's going to make lithium hydroxide. And since this is happening in water, that would be aqueous. So what happens is that each water molecule is going to lose 1 hydrogen, and 2 of those will get together to form this, and then we'll have 2 hydroxide ions left. So balancing this, here's lithium and lithium, 1 oxygen, but over here I have 3 hydrogens, and there I've got 2 hydrogens. If I put a 2 in front of the lithium, I've got 4 hydrogens, and then I can put a 2 over here to get 4 hydrogens. I've got 2 oxygens, and I put a 2 over here. That one's hard. Gaseous hydrogen and liquid bromine. So H2 gas and liquid bromine. Bromine is also one of the diatomic elements. What do you think? Well, it's going to have to be hydrogen and bromine together, right? There aren't any other elements. So it's going to have to be H and Br somehow. Have we seen a compound with hydrogen and bromine together? Hydrobromic acid. Molecular compound, but forms ions in water. What ions does it form? Br minus and H plus. And so that's going to make HBr. That is a gas. I wouldn't expect you to know that. And then to balance it, we just need to slap a 2 on there. What? Yeah. They explode. Yeah, the alkali metals, lithium, sodium. Well, lithium not as much, but sodium and potassium and rubidium will definitely explode in water. That's why you don't see, silverware made out of sodium. Right? Yeah. Dip the spoon in the soup, kaboom, right? Not so good. Trends in the noble gases. Increasing atomic radius, boiling point and density going down. The ionization energy decreases, but it's very high. These guys are exceptionally unreactive. In nature, we only find them not combined with other elements. We use them as an inert atmosphere. So, how could you keep sodium from reacting with stuff? Well, you could put it in a container and flood the container with a noble gas. The sodium's not going to react with that. It'll just sit there. Before the 1960s, there were no known compounds of noble gases. And I'm pretty sure helium, still no compounds known.